sir.
Oh. Okay.
Okay, sir.
Yeah. Okay. So Google means YouTube means this is an online link.
Yes, sir. Online link, sir.
Okay.
Live streaming is there, sir, in YouTube.
Okay. But are you recording this thing?
Yes. Yes, sir.
But you have to take consent, right, from the people like before recording. No, I did not find anywhere that okay you are going to record this part.
Yes, record.
Sir, we have YouTube videos, sir.
YouTube will it be recording?
Recording, sir. In YouTube.
No, in YouTube is it recording?
Yes, sir.
But that should be avoided.
Okay, sir.
Record చేయొద్దండి అంటున్నారు సార్.
Okay, sir. We'll delete, sir, after.
After this session, we will delete we will delete that content, sir. In today's session.
It's okay, no problem. Okay, we'll discuss on that part later. Okay, let me start my presentation first.
Okay.
I will share my screen.
1 minute, sir. Sir, 1 minute, sir. We will introduce.
Okay.
Respected dignitaries, participants from the various institutions, and my dear colleagues, a very warm welcome and good morning to one and all. I, S. Reshma, Assistant Professor, Department of EEE, delighted to welcome you all on behalf of Gates Institute of Technology for the 5 days faculty development program on emerging trends and challenges in renewable energy systems, organized by Department of EEE, Gates Institute of Technology, Gutti. Now I would like to request to co-convener E. Ramakrishna sir to give a brief introduction about the day 4 speaker of this program. Thank you, sir.
It's my pleasure to introduce today's eminent speaker, Dr.B.Ravi Kumar sir. Sir has completed his PhD from IISc Bangalore and is currently working as a professor in IIT Hyderabad. To his credit, sir has published more than 25 international and national journals and 65 international conference papers published. Sir has published 2 book chapters. To his credit, sir has 1 DST project and 3 consult projects. He has supervised 3 PhD students and is supervising 6 research scholars. Thank you, madam, for giving this opportunity.
Now I request today's speaker, Dr. B. Ravi Kumar sir, to take over session on renewable energy integration and challenges and improvement.
Thank you all for the brief introduction about myself. Okay, so and also congratulating the Gates Institute of Technology for organizing these type of FDPs for the benefit of many faculty, students, researchers, some type of industrial people. Okay, so now I will go ahead with my presentation. Okay, so let me share my screen first. You're able to hear, you're able to hear my voice clearly.
Yes, sir. 1 minute, sir. Yes, sir. Your screen is visible, sir.
Yes, yeah.
Okay.
Yeah. So we have roughly around 1.5 hour time. Okay, so
Yes, sir.
yeah. Okay, so today's topic is renewable energy integration. Okay, so what are all the challenges and how to improve the renewable energy integration? Okay, so this is the topic of today's presentation. So in this one, okay, initially we will have some brief introduction. Okay, so how these renewable energy sources will be connected to the grid. Okay, so what are all the challenges that we'll be facing, and what are all the initiatives or opportunities that we are having in Indian scenario, and what are all the limitations. Okay, so while connecting these renewable energy sources to grid, And in that attempt, okay, so our motivation is to successfully connect the renewable energy sources to grid. Okay, so then in that aspect, okay, so we tried some research work in that direction, and I would like to present one of our PhD students' work here. Okay, so so you can see here, like, okay, so we have the typical power system, or the transmission network, generation system, and distribution system. This is the typical electrical system. Okay, so the power will be generated at these generating stations, and transmitted to these customers through this complex network. Okay, so now the generation installation is also happening, and the load requirement is also happening in a quite exponential way. But to cater to these loads, it's also expanding in a way. Okay, plans are being made to cater to the future load demands, but in the similar manufacture, okay, the transport network expansion is not happening. Okay, so because of this one, what is happening? Most of the times, the transmission systems operate in quasi steady state mode. Okay, so there are some of the issues with these current power systems are like, okay, quasi steady state operation of the transmission line, which is one of the bottleneck for transmitting bulk amount of the power to the customers, and increasing the energy needs at these customer locations, and peak load shortage and fossil fuel depletions are one of the issue, power quality and reliability issues, and rural electrification. Okay, so these are all some of the issues currently the power system is facing. Then how to meet this demand? Okay, so the previous, whatever the network, whatever it is there, this can be in a way, okay, so we can represent in this fashion. Okay, so where, okay, so this is the generating station, this is the utility grid, and this is the distribution network where you will be connecting some type of household applications, or industrial applications, or some type of distribution side, primary distribution, secondary distribution, all those things will be there. But how to meet this load with these type of issues in the power system? Okay, so how to meet the growing demand for the electricity is the major concern. Okay, one way to accommodate this one is, okay, connecting some type of renewable energy sources to the grid. Okay, so that way, so we can accommodate the previously mentioned issues with the power systems. Okay, so but again, okay, so when you are connecting this local generation to these utility grid at this location, okay, so still again the bottleneck part of the transmission network is still under investigation. Okay, so it is still not met. We are not in a position to uh, address the issue of quasi steady state operation. Okay, so another way of connecting this renewable energy sources is, okay, so it can be renewable energy sources, can be distributed energy sources, can be a PV or wind, or some type of fuel cells. Okay, so these things. Okay, so instead of connecting to the utility grid, if you are connecting to the distribution network, so where the local generation is being used to meet the local load requirement. That is what it works on the principle of local power generation to the local loads. Okay, so this is the concept of uh, microgrid integration, renewable energy source integration to the distribution network. So this way, the power requirements at the local loads will be addressed by these renewable energy sources which are connected to the distribution side. Okay, so here I just want to show you one South Indian scenario. Okay, so where, so the profile of the solar is being there here. Okay, so here the profile of the wind is also being there. Okay, so this is the southern part of India, faces mix of tropical dry and wet climate. Okay, so this is one place in Hyderabad. Okay, so on one of the IT corridor. Okay, so there we identified this type of profile. Okay, so if you see the solar radiations, so average solar radiation of 5.34 kilowatt hour per meter square is available. Okay, so with a maximum radiation of more than 6 kilowatt hour per meter square. And wind profile, if you see, okay, so the is also appreciate that. Okay, so it is look average wind velocity is around 4.14 meters per second. So now if you observe these, I just wanted to check. Okay, so things are fine, right? Okay, you're able to hear my voice, madam. Hello. Okay. So in between, okay, so sometimes you make some disturbance. Okay, so as that I will be in a position to check that. Okay, you are. I am connected to the net. Okay. Yeah. Yeah. From this wind and solar data, it can be observed that, okay, so during these June, July, August, and September, okay, during this time the solar irradiation values are less, but during the same time, if you see, the profile of the wind velocity is more. Okay. So now from these two graphs, we can say that, okay, so if you properly make use of these available PV and wind, okay, so more or less, okay, so we will get a total energy available almost constant throughout the year. Okay, so even though they are all like average values, but if you can plan it in a proper way, okay, so we will have these total energy available almost constant throughout the year. Okay, so now apart from these geographical geographical advancements, okay, so government initiatives are also there. Okay, it started like Electricity Act 2003, where it has given a thrust to the distributed generation in the context of rural electrification, and the rural energy needs are to be catered by a combination of conventional and renewable energy based microgrid. This is the act, it says. Okay, and there is a national electricity policy. Okay, so it also says like it is an extension to the 2003 Electricity Act. Okay, so importance has been given for the reliable rural electrification system through standalone or decentralized distributed generation facilities where the utility grid is not feasible to the extent. Okay, so that is the electricity national electricity policy 2005, it says. And diesel abatement scheme, okay, so majorly to reduce the content of diesel usage is the prime aspect of this diesel abatement scheme. Okay, so in this scheme, it tries to promote the augmentation of the capital diesel power plants with the renewable energy sources to reduce the pollution and generation cost. So in this scheme, okay, the government of India bears around 40% of the total installation cost, and for non-profit making organizations, and for profit making organizations, it gives around 30% of the um, cost, installation cost. And there is a solar energy scheme. Okay, so where this scheme tries to promote the PV generation plants. Okay, so the financial subsidy as like, okay, 30% subsidy for the of the total cost, or 5% of the interest on loan, or 80% of the benchmark cost. Okay, so like that, there is a solar energy scheme is also there, and there are other schemes, okay, to promote these rural electrification, like Rajiv Gandhi Gramin Vidyadikaran Yojana. Okay, so there are to promote the to electrify the remote villages. Okay, so the Rajiv Gandhi RGGVY. Okay, so this is one more scheme. Okay, so these are all the government schemes that have been also available to promote the renewable energy source content, okay, into the grid. Okay, so now we have, when it comes to the Indian scenario, okay, so we have ecological opportunities. Okay, so where if you can properly plan the solar and wind, okay, so almost throughout the year we will have some constant power is being available on an average. Okay, so and also the government initiatives are also there in terms of various acts and policies. Okay, so now Ministry of Renewable Energy Integration is also working on mandating minimum renewable energy content in commercial establishments, universities, industries, which you most of you must be aware of. Okay, so on the residential complexes, government buildings. Okay, so they are pushing some amount of renewable energy should be being generated from these establishments. Okay, so that way the MNRE also promoting microgrid development in India. So this is some statistics, okay, which I just want to show you some old like 2022 December. Okay, so the total installed capacity in India, if you see, okay, so the coal is around 204 gigawatts, and renewable energy source content is almost like 121, almost like around 30% of the renewable energy source content is there. Okay, so in that one again, the hydro is not considered, gas-based things are not considered. Okay, so hydro, without considering hydro, okay, we have renewable energy source content is almost like 30%. Okay, and in this picture, in this graph, if you see the renewable energy installed capacity, the growth of renewable energy source installed capacity over the year, like 1999 to December end, if you see, you can more or less, okay, aggregate this one like a exponentially growing. Okay, the percentage point of view also almost like we can see that exponential growth is there. Okay, but there are integration of the renewable resources, like the renewable energy sources operating like islanded mode of operation is fine, but when it connects to the grid, okay, so it faces some type of technical challenges. Okay, so in performance aspects of the microgrid. Okay, so integration of the renewable energy source based microgrids to the utility grid leads to numerous operational challenges that are to be carefully addressed for the seamless integration. Okay, some of these type of challenges are like power quality and reliability, challenges in the power quality and reliability, challenges in the frequency and voltage stability, challenges in the grid synchronization, challenges in the system protection due to bidirectional power flow, challenges in the power balance, challenges in the economic dispatch, challenges in the system control. Okay, so these are all some of the challenges, like power quality and reliability point of view. If you see, whenever the regular distributed energy sources are there, okay, so they don't introduce any type of harmonics, major harmonics. But whenever these renewable energy sources are connected to grid, majorly they will be connected through by using some type of power electronics based voltage source inverters. Okay, so the power quality generally it will be defined as in terms of harmonics, in terms of sag, swell, frequency deviation, all those things. Okay, so whenever these power quality based, power electronics based voltage source inverters, they are connected to the grid. Okay, so they inject harmonics into the grid. Okay, so which needs to be taken in consideration in terms of various PWM techniques to reduce the harmonics. Okay, so some type of control logics you have to use it to improve the voltage sag and swell during the disturbances. And from the reliability point of view, if you see, okay, so this reliability can be defined in terms of system point of view reliability and network topology point of view reliability. Okay, so system point of view reliability, whenever there is a problem occurs, okay, so these things tries to disconnect from the grid. Okay, so then system reliability comes into picture. From the network point of view, if you see, so they use some type of communication to properly operate these renewable energy sources. Okay, so if there is any reliability issues are there, then it also causes the typical operation of the renewable energy source connected to grid. Okay, so again, challenges in the frequency and voltage stability. If it is a conventional power system, whenever there is a fault or disturbance occurs, the energy stored in the huge mass will be used to counter for these frequency oscillations. Okay, so again, whenever there is a disturbance, then these voltage stability aspects comes into picture. There is a the voltage variations will be there. Okay, so which may lead to voltage instability problems. Okay, so which can be addressed, okay, quite easily when it comes to the conventional systems where these excitation controls will be there. Okay, so but such type of thing, like because whenever you are connecting the energy sources to the grid through these power trans based voltage source inverters, okay, so it immediately whenever there is a fault, they try to safeguard themselves, they disconnect from the grid, which will make the system unstable. Okay, so then there are challenges with the frequency, and again, voltage instability comes because of the availability of the renewable availability of the reactive power during the disturbance time. Okay, so to counteract for that one, excitation control which will be there in the conventional thing, but when it comes to the RS based things, okay, so such type of thing has to be come from the control logic. Okay, so there are challenges in the frequency and voltage instability and grid synchronization. So whenever these renewable energy source based systems, when they have to connect it to grid, continuously they have to monitor the PCC bus voltage, phase angle, and frequency, all those things. Okay, so there the monitoring of the grid is also an important, and maintaining the synchronization with the grid. So accordingly, supplying the like if you have excess power, okay, so sending the power to the grid. All those things more or less depends on the monitoring of the grid. Okay, so grid synchronization and monitoring, there are challenges and challenges in terms of the protection due to bidirectional power flow. Generally, the distribution system wherever these renewable energy sources are connected, okay, so mostly they are like, okay, so one directional thing, like fault occurs, okay, so you can more or less you can say that, okay, so from the PCC it will be from the substation the power is being fed to these faults, but whenever you have the renewable energy sources are distributed energy sources, okay, so the path of the fault also will change, and the amount of contribution from both the sides will change. You can see that there is a bidirectional power flow will be there. This also creates some type of challenges in the system protection. And power balance due to renewable energy source uncertainties. Okay, so in the previous slide we have seen, like on an average we will have a constant power being available throughout the year, but because of the variation in the wind velocity in a day, and variation of the solar irradiation, okay, so there are some fluctuations in the power availability. Okay, so and that has to be properly balanced with the use of some type of uh, storage. Okay, so it also introduces some type of challenges in the economic dispatch. If you want to participate in the day ahead markets, okay, so because of the uncertainties in the renewable energy sources, okay, there should be a proper way of planning to be done, okay, if you operate it economically. Okay, so it also introduces some challenges in the economic dispatch. System control, again, active power control, reactive power control, the power balance, okay, so the operation of the system, the PLLs, these are all also introduces some type of challenges. Okay, more or less the technical challenges, okay, so you can list it out. Okay, more or less they fall into some of these categories. Okay, so for the fruitful performance of the microgrid majorly relies on these following factors. Okay, so one is intermittent nature of the energy sources due to their environmental dependency, that's what we discussed, and the design of the suitable power conversion devices, design of effective controllers for controlling the power converter operation, and suitable architecture selection to interconnect all the constituents. Okay, so this is these are some of the factors on which the fruitful performance of the microgrid depends on. Okay, so ineffective addressing of any of these factors will degrade the key performance aspects of the microgrid interconnection to the grid. Okay, so some of the key performance aspects like power quality, reliability, stability, protection, which we have seen just now. Okay, so these will get affected during the disturbances. Okay, so now, so the power quality concerns raised by these intermittent nature, switching devices based nature. Okay, so more or less they can be counteracted with the some of the techniques like intermittent nature. If you can properly manage with the available storage devices, okay, the intermittent nature can be counteracted up to certain extent. The switching device based power transfer converters, okay, so with the advancements in the multi-level inverters, okay, so various types of conversion topologies. Okay, so the THD levels also can be up to certain extent, so can be addressed. Switching device based power transfer inverters issues also can be addressed, but whenever there is a disturbance, the wind or solar based renewable energy based systems, okay, so to safeguard themselves they isolate from the grid whenever there is a disturbance. Okay, so means they provide lesser grid support during the disturbance or emergencies than the conventional. Okay, so that's why, okay, so this is one of the issue which needs to be addressed. Okay, so in that aspect we worked on how to support the grid during the disturbances. Okay, so now again there will be some guidelines, okay, so that needs to be adhered, okay, for the fruitful renewable energy based microgrid installations, okay, such as IEEE 141, IEEE 1547, IEEE 519, see, our Central Electricity Authority. They also impose some type of guidelines, okay, so to be followed for the smooth operation of the entire power system. Hope you are following.
Yes, sir.
Yeah. So some of the standard limits, okay, so on these performance indices, okay, so whenever you are designing some type of controller, some system, okay, so we have to adhere to some of the limits, okay, so here we have listed, okay, some of the indices. So one is waveform shape, okay, so generally we wanted to have this waveform, if it is a conventional machine based thing, okay, so we wanted to have very smooth like sinusoidal waveform, okay, so but power electronics based converters, okay, so they will because of the switching operation, okay, so they little bit deviate, okay, so that's why the deviations, okay, we don't want to have any deviation as per the standard limit, okay, so stability restoration time also should be as less as possible. This is as per this IEEE 1547 standard, okay, so and there is one more thing, rate of change of voltage, okay, so measured in terms of volts per second, okay, so it should be limited to plus or minus 3 volts per second as per the ANSI standard. And voltage deviation, which is measured in terms of percentages, okay, so it should be limited to 10%, okay, so as per IEEE 1547. Positive sequence voltage and negative sequence voltage, okay, we don't want to have any negative sequence voltages. We always wanted to have, okay, so balanced type of operation more or less, okay, so we wanted to have the positive sequence voltages, and voltage imbalance should be limited to 3%, and over frequency and under frequency deviations, okay, so these should be plus or minus 2% of the rated frequency, and over voltage should be limited to 10%, voltage sag should be limited to 40% as per these standards, and spikes, okay, positive spike or negative spike should be limited to 1/3 of the rated thing, okay, so as per the standard, okay, so stability restoration time, it should be as early as possible, okay, so these are some of the standard limits on performance indices, okay, so this needs to be met at any cost, okay, so are very close to these limits, it should be performing, okay. Now when it comes to the renewable energy integration, okay, so we have various types of renewable energy sources like PV, okay, sand, wind, and fuel cells. So out of these things, okay, so PV and fuel cells, okay, so DC in nature, and wind power depending on the type of conversion and from where you wanted to connect to this one, okay, so it can be AC in nature, and but most of the times, okay, so with the local controllers, okay, so you can be connect this one to a common DC bus, and to face this intermittent nature, okay, we generally use these type of DC batteries, okay, so some storage devices, okay, so more or less they are all like, okay, so the content point of view, they are in DC type of nature, okay, so we can have AC sources, DC sources, and loads, okay, so generally some type of primary loads, secondary loads, okay, primary loads generally defined by critical loads, and secondary loads, okay, even they are disconnected for some time is also fine, okay, so we have 3-phase loads, and apart from meeting the local demand, okay, so we wanted to export it to the utility grid, okay, so now we have AC sources, DC sources, and AC loads and AC grid, okay, so now we have to have some type of architecture where the DC needs to be converted to AC, okay, so which is the requirement of the PCC or the local loads, okay, so we have various architectures like AC bus architecture, DC bus architecture, hybrid bus architecture, okay, so here in this particular case we are making certain assumption from the point of amount of wind power available, okay, in this particular case we are considering the wind is also being converted to DC and connected to a common DC bus, okay, so now we need to have a DC to AC power conversion, okay, so now how we can have the DC to AC power conversion, Okay, so if you see the conventional, like nowadays we are having these power trans based voltage source inverters, but before that, okay, so now there is a lot of advancements have been happened in terms of power trans converters, but before that the conversion used to happen like renewable energy sources connected to a DC motor or motor generators that will be there. Okay, so which will be used to connect it to it connected to local loads. Okay, so this is, we'll call it as a rotary inverter, where okay, so real machines will be used to convert the DC nature to the AC requirement. Okay, so the problem with this type of conversion is limited efficiency. Okay, so this type of conversion we will call like rotary based type of conversion or rotary inverter. Okay, in our comparison purpose with the proposed method, proposed approach. So this type of approach will have limitation in the efficiency, so space requirements. Okay, so suppose it will be fine with small amount of power conversion, but when it comes to the huge power conversion, okay, you require huge space. Okay, so deployment cost for low to medium range load centers. Okay, so this is majorly limited to low to medium range load centers, but it cannot be extended to higher power level conversions. Okay, so now another one is static inverter, where this is regular C. Okay, so the inverter DC to AC conversion by using power trans converters. This is happened because of the power trans devices in the microgrid design. Okay, that has given birth to the several modular and efficient installations all over worldwide. But this gives serious power quality concerns and inertia issues. Okay, so these are some of the things which we have seen in the previous slides. Okay, so the problem with these type of conversions are like, so power quality issues and inertia issues. Okay, so power quality issues more or less you can control with the converter topologies and control logics, PWM control things, but inertia issues needs to be addressed. Okay, so which is a challenging task faced by nowadays researchers. Okay, so if you see the rotor based electrical machine based conversion, the control will be like, okay, so if you are using this type of conversion, the synchronous generator control will be there. Okay, so excitation control and the mechanical power control will be done at the DC motor level. Okay, so and here left side we are having various renewable energy sources like PV, wind, fuel cell, along with their local um, converters. Okay, and if you want to convert these hybrid renewable energy sources to the uh, uh, control system that will be there in the power trans based conversion. Okay, now if you compare these static and rotor based converters, okay, so some of the matrices you can see in terms of performance indices, operational efficiency point of view, and general features point of view. Okay, from the power performance indices point of view, if you see power quality, moment of inertia, stability, resiliency, and frequency response and voltage response, these are some of the indices which will be taken under the performance indices matrices. Okay, so if you compare the static inverter like power trans based inverter and DC motor coupled synchronous generator based inverter, okay, so the performance indices point of view, you can see these things are good, like green color. Okay, so like power quality, real machine like synchronous generator based machine, conventional based machines, they work better. Okay, so power quality is good, moment of inertia capabilities are good, stability point of view they are good, resiliency point of view also good, highly stable frequency response, voltage response. But the power trans based, they utterly fail in this particular case. Okay, from the operational efficiency point of view, if you see life period, the power trans based converters, they have more life period as compared to rotating machine based thing. Power conversion efficiency is higher and system maintenance is very low, and speed of response is higher. Okay, so in that aspect, okay, so the static inverters are competing ahead as compared to the DC motor based synchronous generator. And from the general features point of view, if you see implementation cost is low here, space requirements are also low here. Suppose if you 10 kilowatt conversion system, if you take it, okay, so the size of these power trans based converters are the space requirement is less as compared to the similar type of conversion required from the rotary based inverter. And filter requirements are required here, but here it is not required. But rest of the other things, if you see, design complexity is less, unit size is less, acoustic noise is less, okay, they generate less noise, okay. And applications, okay, so it is suitable for all load centers. But if you go for 1 megawatt conversion, it is very highly difficult, and the conversion efficiency is also lesser in case of rotary based conversion. So that is what we have seen in the previous two slides. So now, so looking at these two things, okay, so the rotary based converters, they are good in terms of performance indices, but the static converters, they are good in terms of operational efficiency and general features point of view, okay. So now looking at, after having literature survey and looking at these type of comparison between static and rotary based inverters, we identified, okay, so for specific applications rotary based inverters are good, for specific applications static inverters are good. But combining these two things, if we are having, that is a very good conversion, okay. So why not we try in that direction, okay. So there we started working on how to get both the features, like performance indices as well as operational efficiency point of view, general features point of view, okay. So why not we have a one converter which can give beneficial performance, okay. So in all the aspects, okay. So now, okay, so we have DC based sources and AC requirements, okay. So now the power converter, if it can behave as the way static converter, if it behaves as the way rotary based converter, so which can be achieved by using a control system, okay. So now these selection of the architecture, converters and control, okay, so these things, they play a major role in the improvement of the performance of the microgrid, okay. So so we, so with that aspect, okay, so with that aspect of achieving both the benefits from the static converter and rotary based inverter, okay, so we started thinking and proposed a methodology, okay. So a system where, okay, so why not we have these DC motor coupled synchronous generator model in the control logic itself, okay. So then we may achieve, okay, so both the benefits, okay, so all the three performance merits, okay, so in a single converter, okay. So in that aspect, okay, so this is the proposed structure, okay. So one of the PhD student, he worked on that and he got PhD and good publications he got it, okay. So renewable energy based sources are there, okay, so which is DC in nature, and inverter is there, and there is a AC so requirement is there, okay. So now from the AC side it will take feedback, and from the DC side also it will take feedback, and inside, okay, we are having the DC motor coupled synchronous generator, which is a virtual DC motor based synchronous generator. This is a model, this is not real machines, okay, but here it is a these are real machines, okay. So these real machines based model, if it can go into the control system, okay, so the way the real machine based system is operating, that can be mimicked, okay. So in this static inverter, that is the idea we wanted to implement here, okay. So now that's why we are calling this one as a closed loop virtual DC motor coupled synchronous generator based control scheme, okay. So this is the implementation point of view, okay. So we have the renewable energy sources, they are connecting to a DC bus, 600 volts DC bus, by using their local controllers, and here we have a 400 volts AC thing, and which is being connected to utility grid 11 kV by using some type of step up transformers, and this we have considered like a point of coupling. And here we have some type of building loads, okay. So like whenever it disconnects from the grid, and if you have sufficient sources, okay, it will try to feed the local loads. And this is the typical control scheme that we have proposed, okay. So this is a 3-phase 5-level diode clamped multi-level inverter, okay. So we use sine triangular pulse width modulation. There are 4 carrier signals are there with a frequency of operation of 1 kilohertz, and each one is having a amplitude of 2.5. So the modulation signals are having 50 Hz frequency and amplitude of total 10. And by using these closed loop control scheme, okay, so we will be generating these I reference ABC. Okay, so this is I reference ABC. So here it is taking the measurements at the 400 volts AC. Okay, so VABC, IABC it is taking, and they will be converted to DQ components. So that will be fed to the excitation control. So here you can see that there is a synchronous motor model is there, and there is a DC motor model is there. DC motor model is being fed from the signals from the DC bus. Okay, it is being fed from the signals. Okay, not the electrical quantities. This is not the electrical power. This is only a control scheme. Okay, so where it operates in with the signal values. Okay, so the DC motor, shunt motor will be fed from VDC positive and VDC negative. Okay, so whenever there is any fluctuations, or if you want to take feedback from the DC bus, okay, so according to that the DC motor model will operate. And on the AC side, if there is any fluctuations or disturbances, okay, that will be reflected on the measurements, and which will be taken care by the synchronous machine model. Okay, so now we have the DC motor model and synchronous machine model, based on which, okay, so these are all models. Okay, so by using these models, okay, we will be generating the I reference ABC, which is being used for generating the PWM techniques based on the sine PWM technique. Okay, modulation technique. So these are some of the modeling aspects of the DC motor and the closed loop control. And this is the synchronous generator model. Okay, so which you can get it from the standard books. We used only the standard equations. Okay, so because we are using only models, okay, the DC motor models and synchronous generator models, excitation models, these things we have used it. Okay, so now, okay, so this is the detailed signal routing of the closed loop virtual DC motor synchronous generator control. Okay, so VABC is coming from the AC bus, and VDC MG is coming from the DC bus. And so here we have a voltage equation, and there is armature current control, which is being governed by two cascaded PIDs. Okay, so and here you can see, okay, so there is a excitation control and torque equation. Okay, so now whenever there is a fluctuations in the DC side, okay, the DC motor model provides the control mechanical torque. Okay, so now if you see, the torque requirements for the synchronous generator is being provided from the DC motor, and excitation control is used to control the voltage thing. Okay, so now the generated voltage at the synchronous generator, that depends on the speed that is being provided by the DC motor. Okay, so always we wanted to synchronize with the grid, means, okay, so with respect to the grid voltage changes, grid frequency changes, okay, our speed has to be altered. Okay, and also to meet the PCC voltage, the excitation control has to operate. Okay, so in that aspect, the DC motor model provides the controlled mechanical torque, and the exciter model provides the controlled field voltage to the generator. And in that way, the frequency and voltage, okay, so the rotor speed and field voltage are regulated for the various variations in the PCC voltage. Okay, so that way, okay, so the uncertainties in these frequency and the voltage are controlled over wide range. Okay, so this in turn control the I reference. Okay, so I reference ABC, so which in turn controls the firing angles of the inverter and injects virtual inertia into the system. Okay, so this is the concept of the closed loop virtual DC motor coupled synchronous generator in the closed loop path. Okay, so these are some of the specifications that we have used for modeling the DC motor and synchronous generator. Okay, so here these are the DC motor model parameters. These are the synchronous generator model parameters. So we developed an experimental prototype. Okay, so in this particular case, okay, so we did it only for the islander mode of operation, and we have used a DSpace 1104 controller board. Okay, so to sense the sensed voltage and currents values are being fed to this one by using ADC channels, and the proposed logic is being embedded in these controller board. Okay, so based on the logic, it will generate the PWM signals. Okay, so which in turn control the frequency and voltage of the three-phase inverter output. Okay, so in this particular case, for experimental point of view, we have done few verification of the few matrices, but the simulation point of view, we have verified for even for the disturbances and frequency variation faults also. Just a check. Okay, hope you are in sync with me. Hello.
Sir.
Okay, yeah, fine. Okay, so these are some of the experimental prototype specifications. Okay, so these are the we have used a Tata Power PV panel and DSpace models, and these are the IGBT semicron IGBT model parameters. Okay, so another thing also we did it with a NI based PCI card. Okay, so when we are handling with these type of DSpace 1104, apart from this one, okay, we wanted to try with other microcontrollers. Okay, so here we have used NI based PCI card. Okay, so here also we can we use the MATLAB Simulink based real time toolbox. Okay, so the setup point of view, okay, IGBT and diode based three-phase two level inverter unit we have used, and to monitor the output. Okay, so we can monitor on the PC as well as we can monitor on the oscilloscope, and these are some of the equipment that I have used. Okay, so this is a resistor, there is an inductor to change the load. Okay, we use these load modules, and this is the inverter module. Okay, so and this is the target PC where MATLAB is being run, and that is being dumped onto a NI based PCI card, and these are some of the sensors we have used it, like differential probes we have used and current probes we have used. There are some filter requirements are there. That filter design is there here. Okay, LC low pass filter we have used. Okay, so the test case have been generated for various cases, like to verify the THD, to verify the voltage imbalance, over and under voltage validation, and frequency deviations. Okay, these are the test cases. 4 test cases have been generated. Okay, so to test the simulation. Okay, so in the simulation, okay, to test it. Okay, 4 cases have been considered for the experimental validation. We used 3 cases, but here the frequency deviations we have not done it because we have not connected to a grid. Okay, so this is only islanded mode of operation for the experimental verification. Simulation we have done it for the grid connection also. Okay, so now while testing, okay, so the procedure also should be as per some standard. Okay, so the standards, they define how to test the THD. There is a procedure. Okay, so according to that procedure, okay, so we have a base load of 250 kilowatt, and what we are doing is like injecting a dynamic 3-phase load in terms of 0 to 30 kilowatt and 0 to 20 kVAr, okay, into the renewable energy based microgrid. Okay, so whenever these type of load variations are there, okay, so P variations, Q variations are there, okay, how these THD is being varied. Okay, so that is one test. And voltage imbalance, how it is being affected. Okay, so when you are injecting a reactive load unbalance, okay, here we have considered phase A. Okay, so at around 0.03 seconds we have created a unbalance. Okay, reactive power load unbalance of 50 kVAr is created. Okay, so and to check the over voltage and under voltage indices, okay, a large capacitive load is being switched on and off, and again inductive load is turned on and off. Okay, and frequency deviations to measure it. Okay, so the single line to ground fault at load bus is created, So these are some of the test cases. Okay, so by using which we checked for these indices. Okay, which one is better, and for the analysis of the power quality analysis through experimental setup. Okay, reactive load variations we did it. We have load banks by using which we have reactive load variations have done. Okay, unbalanced loads also have been done on all the three phases, and signal shape. Okay, how the shape of the voltage waveforms. Okay, so we have seen. Okay, so like that we have created total 7 cases. Okay, for simulation as well as experimental. Okay, so these are the simulation results. So used FFT available in MATLAB. Okay, so in the case one we are injecting a 3-phase load and try to vary the real and reactive power. Okay, so the proposed closed loop operation. Okay, so based inverter. Okay, it is generating 2.54 percentage as compared to the 3.3 percentage of the conventional diode clamped multi-level inverter based conversion. This is another case to check the voltage unbalance. Okay, so in this part we are injecting a reactive load of 50 kVAr at phase A. Okay, so it is created at 0.03 seconds and up to 0.06 seconds it is been there. Okay, so at 0.06 second it is connected to grid. Okay, so now here if you see voltage unbalance. Okay, so it is voltage imbalance is measured in terms of negative sequence quantity to the positive sequence quantity. Okay, so we know that the negative sequence quantity we don't want to have it. Okay, so as less as possible. Okay, so means okay the voltage imbalance percentage as less is that much better. Okay, now here blue one is there, which is a conventional diode clamped multi-level inverter, and there is a gapped lines are there. This is a DC motor coupled synchronous generator. This is a real machine. Okay, so rotary inverter. This is a static inverter, and this is the proposed method. Okay, so where closed dotted lines. Okay, so here you can see that. Okay, so in all the cases, okay, even when you are connecting to grid, also the voltage imbalance percentage is less for the proposed method. So this is the over voltage and under voltage for the test case 3, where in this particular case the capacitive load and inductive loads are being turned on and turned off. Okay, and so this is the instant at which the capacitor load is turned off and here turned on. Turned on and turned off. Here again inductive load is turned on and turned off. Okay, so even here the red color one. Okay, so here there is ideal case is also there. Okay, so microgrid voltage always should be very close to 1 per unit. Okay, so whenever you are connecting some type of converters, okay, so as long as they maintain close proximity to the ideal case, that is better. So here the red line is closer as compared to the blue line and green one. Okay, so which also shows that the proposed method is operating closer to the ideal cases. And this is the case with single line to ground fault. Okay, so here you can see the clear discrimination between the conventional static inverter to the proposed static inverter. So the red one is a rotor based rotary based conversion, and green one is a proposed conversion, and the blue one is conventional DC motor coupled synchronous generator, as DC motor diode clamped multi-level inverter. Okay, so here the frequency variations are higher as compared to the other two methods. Okay, so now if you compare the harmonic spectrum of the experimental results. Okay, so here you can see that the diode clamped multi-level inverter THD is 15.81, whereas the proposed one is 7.7. For when you are applying a load of 75 ohms plus 80 millihenry real and reactive power load on each phase, and the wave shape of the voltage also if you see. Okay, so for this test case 6, okay, this is with the conventional diode clamped multi-level inverter. This is with the proposed closed loop operation of the DC motor coupled synchronous generator. Okay, so here the wave shape is also very close to is improved as compared to the conventional one. Okay, so now if you compare these performance analysis of the conventional as well as proposed. Okay, so for all these 6 cases, so this is the conventional static inverter, and this is the rotary based inverter, this is the proposed inverter, and here we have listed the limits. Okay, so now as per the standard it should be 8%, and all the 3 are being met out of those things. Okay, so the proposed method is lower. And when it comes to the voltage imbalance point of view, so these 2 things they violated, this is well within the limits, and over voltage are lesser, and here rate of change of frequency is very less as compared to the conventional machine based things. And from the hardware experimental set point of view also, these values are lesser, this is lesser, and this is it should be wave shift should be pure sinusoidal, but it is less distorted as compared to a conventional DC motor coupled synchronous generator. So now it is 11:30. Okay, so shall I continue for a few more minutes, or shall I stop it here?
You can continue, sir.
Yeah. Okay. Yeah, there are various other virtual synchronous generator frameworks available in literature. Okay, so these are some of the frameworks that are available. Like this is a vSync project. Okay, so topology. Okay, so this A1. Okay, and there is a IEP based VSG topology. Okay, so this is a Kawasaki Heavy Industries based voltage source inverter topology, and this is Professor Ise. Okay, so they developed some topology. Okay, so Ise Labs topology. Okay, so if you see these first one vSync based topology. Okay, so it is it uses a PLL, which is differential equations based PLL. Okay, so that is used in the operation of power based voltage source inverter control loop. Okay, so also used the energy storage systems to mimic the dynamic behavior of the synchronous generator. So the limitations of these topologies, like the dynamics of the synchronous generators are not considered in this VSG control loop design. Okay, so because of this one, what will happen? Okay, it cannot emulate the dynamic behavior of the synchronous generator, as it operation depends on the storage system's charging or discharging times, which are not analogous to electrical machines. And this is another approach. This is IEP topology. Okay, so in this one, the synchronous machine model has been used. Okay, so in this thing, okay, so by the development and the use of the synchronous machine model in the it is used, and the limitations is like in this one there are some inputs like the mechanical torque and excitation voltage, which is considered as constant. Okay, so because of this constant nature, okay, so it cannot cope up with the real-time disturbances, okay, effectively. So this affects the efficiency of the control system, and it is difficult to maintain the frequency and voltage stability during disturbances. Okay, so that is the limitation of these IEP's topology. There is another approach, KHI's VSG topology, Kawasaki Heavy Industries topology. This is a little bit detailed as compared to the previous 2 frameworks. Okay, so this control loop is having 3 submodels. Okay, so one is for the PLL, and there is a AVR model, automatic voltage generation, and there is a governor model. Okay, so this PLL, okay, so it is taking it is sensing the V grid. Okay, from that one it generates the theta, and so there is a current generator, like this is used to generate the reference signals, and there is a AVR which gives the EF, and governor model will give the omega R. Okay, so here also it requires the Q information, omega naught information, V reference information, and delta P. Okay, so so again, okay, so these things also they have considered as these information, these practical values information is required. Okay, so which are assumed values rather than practical values. Moreover, the variations of these powers with respect to load variations or any disturbances, okay, so they have not considered in these assumptions, and so the scheme may not cope up with the actual powers varied by load changes in real time, which impacts the performance of the control loop. There is another topology. Okay, so based on this VSG, this is a ISA slab. Okay, so this in this approach, okay, so they used swing equation based topology. Okay, so control logic. Okay, so by the development of swing equation based control logic in the PVSI's control loop. Okay, so they developed this VSG. Okay, so here the P in is required. Here you can see that P in is required. Yeah, so P in Q star. Okay, so they assume the active power reference as well as the reactive power reference for the synchronous machine operation, which affects the overall control system's performance. Okay, so apart from that one, okay, so there is a PA based controller methods for QE loop is also being used. Okay, and because of the limitations of the PA control logic, okay, so ineffective for non-linear disturbances and difficulty in PA gains tuning and all. Okay, so these are some of the limitations of these ESS lab VSG topology. So now, okay, so among these topologies, generally people they compare with the IEPS topology. Okay, so to check the proposed topologies. Okay, so now for the comparison purpose, various test cases. Okay, test case 1, 2, 3, 4 has been done for simulation studies, and for experimental studies, test case 5 to 11 has been considered. Okay, so various performance indices are like three-phase voltage waveform checking and voltage deviations and frequency response have been considered for simulation studies, and harmonic distortion limits, voltage sag and drop, voltage spike, and voltage imbalances have been considered for the performance indices validation. Okay, the type of disturbances. Okay, so when it comes to the three-phase voltage waveform, balanced load variations and non-balanced non-linear load variations have been considered. Okay, so for voltage deviations and frequency response, non-linear load variations and have been considered. Okay, so base load have been considered 25 kilowatt plus 6.25 kVAR with 0.97 lagging power factor. The simulation has been run for almost like 160 seconds. Okay, so and the test loading has been done during these time periods. Okay, so when it comes to the experimental startup, okay, we consider the duration like, because when you are doing this type of imbalance, unbalanced reactive power and all. Okay, so we have limited our things for few milliseconds, and within this time itself, okay, we wanted to capture the waveform and try to analyze. Okay, so in this particular case, around 200 watt plus 200 var. Okay, so with 0.7 lagging power factor have been considered as a base load. So this is the case. Okay, so where here, okay, so we have considered at this is the simulation results. Okay, so at around 125 seconds, okay, so a 0.7 power factor leading load is connected. Okay, so during that time we wanted to check what is the voltage spike peak value. Okay, so in case of IEPE, okay, we can see around 1350 volts is there. Okay, so in case of proposed method, 1120 volts spike is there, and and this is the instant at which electrical arc furnace load is on. Okay, so you can clearly see the waveform shape of the conventional IEP method and the proposed method. Okay, so the waveform distortion is also limited in case of the proposed method, and this is the instant at which electrical arc furnace load is off. Okay, so the conventional method, you can see that. Okay, so the immediately the electrical arc furnace load is off at 90 seconds. Okay, the waveform got distorted, and to come back to the normal operation, it took almost like 2 cycles, but it is very instantaneous in the case of proposed method. And voltage deviation, conventional IEP is having 4.9 percentage, and whereas the proposed method is limited to 0.5 percentage. So and this is the case where, okay, instant at which load is on and off. Okay, here we have zoomed it here. Okay, the frequency variations. Okay, so in the conventional, the lower dip is touching the 49.8, and at instant 2 it is touching 50.25. But in case of the proposed method, the frequency deviation is well less than 49.9, and in the second instance, okay, it is limited to 50.1. Okay, so you can clearly observe the difference of frequency deviation, and these are from the experimental results. Okay, the top ones are the IEP methods, and bottom ones are the proposed methods. Okay, you can clearly see the differences. Okay, in case of THDs, for the test case 5, 3.58, for the IEP, for the proposed method is 1.85. So same thing, you can see it for the test case 6 and test case 7 also. The THD percentage is lower as compared to IEP method. And these are for the test case 8 and 9. Okay, so where impedance load is changed and single phase unbalance has been created and a two phase unbalance has been created. Okay, so here you can see that, okay, the SAG values are also less here as compared to IEP. And here the imbalance is also like 10.5% imbalance. Okay, so here it is 2.45. So in case of two phase unbalance, 7.79. Okay, so proposed method is 3.16. So if you summarize all the results in a tabular form, okay, so except for the test case 1 and test case 11, okay, so rest of the things, okay, even test case 11 also, okay, so it is just crossed 3%, 3.16. Okay, so whereas the IEP method is 7.79. Okay, huge variation is there. But in the case of voltage spike, okay, so definitely it requires some type of improvement. Okay, so rest of the parameters, okay, so the proposed method is well within the limits of the standards and well ahead when compared to the other schemes. So the salient features of the proposed control scheme is like this scheme perfectly mimics the behavior of the conventional electrical machines based power plant, and because of this closed loop operation, it can cope up and operate, tolerate the real-time uncertainties, and it operates as close as like the conventional rotary based inverters. Okay, so means the emulation of the dynamic behavior of the electrical machines is being incorporated in the closed loop. Okay, so because of that one, it improved the moment of inertia, and it enhances the capability of the loads to stay connected with the local or grid power supply during the uncertainties. Okay, so from the simulation and experimental results, what it can be seen, like we can say that we can conclude that under different conditions, the proposed scheme shown improved power quality, which in turn improves the resilience of the microgrid. Okay, so overall, the improvement of the power quality offers opportunity to integrate the renewable energy based microgrids with the utility grid. This will help in getting stable, continuous and reliable power supply through the adherence to the various standards, regulations imposed by various grid codes or on the microgrid regulations. Okay, with this one, okay, so I would like to conclude my presentation. Thank you all. Any questions can be taken up at this moment of time for discussion point of view. Yeah.
Thank you, sir.
Yeah.
So any queries, please comment in the comment box.
Nice presentation.
Thank you.
Now, vote of thanks on behalf of the Tribly department. Today, I take this opportunity to express all my gratitude in the form of words. First of all, I would like to thank our today's eminent speaker, Dr. B. Ravi Kumar Garu, for accepting our request and for giving such a wonderful presentation on renewable energy integration and challenges and improvement and making event meaningful and interesting. Thank you very much, sir.
Thank you.
I would like to express our profound gratitude our correspondent Srimati V.K. Padmavatama Madam Garu, Managing Director Raghunath Reddy Sir Garu, Director Sri Vani Madam Garu, and Principal Director Sayed Surya Madam Garu, Convener, and this entire team for their constant support and encouragement. Thank you, one and all. Finally, at the end of this section, I would like to thank all the participants in this FDP for their glorious presence. Thank you, one and all.
Yeah. So any queries?
I think we don't have any queries, sir.
Okay, fine. Yeah.
Thank you so much,
So,
sir.
Thank you so much,
there are
sir.
no queries means people they understood, I feel.
Yes, sir.
Thank you so much, sir.
Thank you
Once
so much,
again.
sir.
Yeah, thank you. I will leave the call.
Sir, shall I close the sir? Close the
Yeah.
session?
Miss, if you want to have a discussion, you can have it. But if you want me to disconnect it, I will disconnect it.
Right, sir. Yes, sir. Thank you, sir.
Thank you very much. Have a good day.
Thank you, sir.